Okay, little more complex is this system where you have one resistor in series with another box. That box contains one capacitor in parallel with the resistor. I am taking up this circuit because this can be used to model a very simple electrochemical reaction under certain assumptions. We assume mass transfer is very fast, we assume the reaction is very simple, straightforward, one step reaction. We assume that the other side has reference electrode, good reference electrode, therefore impedance is nothing, 0. This R1 represents the solution, this represents the double layer capacitance C2, and the R2 here represents the reaction. Sometimes this is called Randall circuit, sometimes mass transfer resistance is also added, and that is also called as Randall circuit. Right now we look at this, we will worry about how to relate kinetics to this later. Right now we want to look at this and calculate the impedance for this circuit. I want to call the left side as 1, the right side as 2. The admittance of the elements in the box is going to be admittance of capacitance and admittance of resistance. So, I will call this as j omega C2 1 by R2, sum of these will give me the admittance of the box. Total impedance, I call it as Z total, is going to be R1 plus Z2, Z2 is going to be inverse of the admittance here. So, I want to take up some example numbers. These are reasonable numbers for an electrochemical system. For half centimeter square electrode, it is reasonable, 20 microfarad per square centimeter is considered normal for a simple electrode. So, this is again a reasonable number. 100 ohms is one example of the resistance coming from the reaction. If I take this, I have to tell this is the frequency, tell me the impedance. So, now we come to the impedance spectroscopy. We are looking at electrochemical system. We are measuring the impedance. Impedance is a coupled quantity, a pair quantity. It has magnitude and phase or real and imaginary part. They are not exactly unrelated. It is not that I give one frequency, I get a real part and imaginary part, I get a phase and magnitude, but these are not completely unrelated. Okay, we will see that again later, but we measure the impedance. Now, you are familiar with what is called spectroscopy. Some of you might have done UV visible spectroscopy. What do we do there? We measure usually absorbance as a function of wavelength. Some of you might have done FTIR, that is Fourier transformed infrared spectroscopy. There you would get absorbance or transmittance as a function of wave number. Wave number is inverse of wavelength. You can say wavelength, you can also plot it as a function of frequency. Frequency and wavelengths are related. So, if we measure a particular quantity as a function of wavelength or as a function of wave number, as a function of frequency, we call it as a spectrum. So, here we normally represent it as a function of frequency f. Sometimes you will represent as a function of angular frequency omega, but most of the time you will see it as a function of frequency. So, we take an electrochemical system, which means usually a 3 electrode system. In case of batteries, in case of fuel cells, you may not be able to introduce a reference electrode. So, because of those practical difficulties, we will use a 2 electrode system, but we normally mean to use a 3 electrode system. So, we use electrochemical system, measure the impedance as a function of frequency. That set of data is called electrochemical impedance spectrum. Now, when you get impedance spectrum, you can visualize I have one column of frequency, I get 2 columns of data, it may be real and imaginary, it may be phase and magnitude. Now, I want to plot this. I can plot it in different ways. Before we go there, I want to look at this circuit. Let us think, what do we expect to see when the frequency is very, very high or when the frequency is very, very low. Typically, we use 100 kilohertz, 30 kilohertz, 100 kilohertz, 1 megahertz at the high frequency in an electrochemical impedance spectrum. Low frequency depends on how long we are willing to wait, how good the system is. We will at least go till 100 millihertz, 0.1 hertz. If the system is good, if we can wait for a long time, we will go to 10 millihertz, we will go to 1 millihertz, we will go to 100 microhertz. The best instruments say they can take data up to 10 microhertz. Now, you also have to think why it takes long time for us to measure at low frequency. If I say 1 millihertz, that means it takes 1000 seconds for one cycle to complete. I need at least one cycle data to get some idea of what the impedance is. The period is inverse of the frequency. So, when I go to low frequency, the period becomes much longer. So, we have to wait for longer time. In electrical impedance spectra, people will normally work with 100 hertz, 1 kilohertz, and they will go to megahertz and gigahertz. In EAS, we normally go to lower and lower frequency because lot of information is present only at low frequencies. So, we want to go to as low as possible, within the time constraint. Now we have an idea of what is meant by high, what is meant by low. High means at least 10 kilohertz, 100 kilohertz, in that range. Low means at least 1 hertz, lower than 1 hertz. So if you go to high frequency limit, what happens? At high frequency, low frequency, at all frequencies, the resistance has the same impedance, it is R, it is 20 ohm. The impedance of a capacitor is going to be Zc is going to be 1 by j omega c. C is a fixed number here. When I increase omega, this capacitance is going to give 0, 0 meaning very small value of impedance. So this will act as a short circuit. So if it gives very little impedance here, this offers a fixed resistance, this offers 100 ohms. If the magnitude of this becomes much lower than 100, if it becomes for example 0.1 ohm, current comes here, all the current will pass through this, almost no current will pass through this. So all the current will pass through this, and this 0.1 ohm can be neglected compared to the 20 ohm here and the 100 ohm here. So I will see only 20 ohm of resistance, 20 plus a small number. So at the high frequency limit, we will get R1. It will be a real number because this will be almost 0. This does not even play any role because it is blocking compared to this. So at high frequency, I should expect to see 20 ohm as the total impedance of this circuit. Now I would like you to guess what we would see at low frequencies. When I say low frequency, let us say 1 hertz or 0.1 hertz. At this level, what will happen to the impedance of the capacitor? When omega is very small, Zc is going to be large. That means this is basically going to block. At low frequency, it is not going to be offering any pathway for current to go through. All the current has to go through this. Let us say omega is in the order of 10 power minus 1. C is 10 power minus 5 because it is 10 microfarad, that means 10 power minus 5 farad, correct. Omega is in the range of 0.1. So this is going to give 10 power 5 ohm or something of that magnitude. So no current is going to go through this, current is going to go through this only. Therefore, the low frequency limit is going to be R1 plus R2, that means for this example it is going to be 120 ohm. Now we can use this formula, calculate the impedance. One way of plotting the impedance is to plot minus Z imaginary versus Z real. It does not appear well here, but the abscissa is Z real, the ordinate is minus Z imaginary, it is not Z imaginary. If you look at the previous calculation, we got a value saying 1 minus 1.59 or so J. Remember, you have a resistant capacitor in series, that is what we got. That means the real value is positive, imaginary value is negative, and most of the time, especially high frequency and middle frequency data, middle meaning like 10 hertz or so, we are going to get data with positive value for the real value and negative value for the imaginary value of the impedance. So usually it is plotted as minus Z imaginary versus Z real. Okay. This is the high frequency data, it is coming to 20 ohm. The low frequency data is coming to about 120 ohms, and these are going to be the mid frequencies. Okay. Another point that I want to note is the frequencies. In UV visible spectroscopy, you would measure from 200 or 300 nanometer at the lower limit to 700, 800, it is going to be every 0.1 nanometer depending on the specification we give. It is linear scale, meaning it will start at 400, 401 and so on. Here it is usually done in log scale, in geometric series. So if I take one frequency, I normally will not measure at 1 hertz, 2 hertz, 3 hertz, 4 hertz, 5 hertz and so on until, because now imagine if I want to go to 10 power 5, I have to take so many data points and it is probably not worth it. Instead, I will take 1, multiply by 1.2, multiply by 1.2 again, it is going to be 1.44, and so on. So, I will reach 10, then again if you multiply it will go in geometric series, that means I can cover from 1 to 10 in, for example, 7 intervals or 6 intervals. So, I will say 7 frequencies per decade, 6 frequencies per decade. If I say 1, 2, 4, 8 and 10, next it is going to be 10, 20, 40, 80 and 100. So, it is going to go in that way, and usually we do not like to take it in harmonics, that is I do not want to take an integer multiple of the base frequency. There are some reasons for that, right now do not worry about it. We want to take it as 1, then a fractional number and so on, 5 frequencies, 6 frequencies, 7 frequencies per decade. More frequencies per decade you have, better. It takes longer time, but you will have more resolution. Normally when you plot like this, I have not given the frequencies, but when you really want to present the data, you have to mark this and say this is 10 millihertz, this is 10 hertz, this is 1 kilohertz. Few points you have to give, otherwise nobody knows what frequency corresponds to which data. Another point to note is these have to be equal scale. If you take 0 to 25, whatever length we have here 2 centimeters, the y axis also 2 centimeters should give me the same number. Many times in publications you will see it is not done correctly, it will be 0 to 20 ohms here, 0 to 200 ohms with the same scale. It will distort the figure. Here when I look at it, it looks like a clean semicircle, it is a clean semicircle. This capacitor is a good capacitor, it is called ideal capacitor. Many times the data will actually come like this, I am not drawing it nicely, but it will be a semicircle which is pushed down. That means this cannot be represented by a simple capacitor, it needs to be represented by a different element. All this information will come only when you plot it in equal scale. Next, this can also be plotted in what is called Bode plot. This plot is called complex plane plot. This is the correct terminology when we use a 3 electrode system and measure the impedance. When you use a 2 electrode system, you can call it as Nyquist plot. Often you will see that this is called as Nyquist plot in the journals, but the correct terminology for a 3 electrode system is to say complex plane plot. You can plot it as a function of frequency. Now look at this, this is 10 power minus 3, that is 1 millihertz, 100 millihertz, 10 hertz, this is 1 kilohertz, this is 100 kilohertz. This is given in log scale. So, frequency in the log scale, pink color line is the magnitude of the impedance, this round blue color points are the phase value, and these are in fact minus of the phase value given in radians, you can represent in radians or degrees. Magnitude is given in ohms, sometimes this is plotted in linear scale like what is done here 0, 50 and 100, sometimes this is plotted in log scale. This representation is called Bode plot. And you can see here at high frequency it settles at 20 ohms, at low frequency it settles at 120 ohms. It is also clear that it settles around 10 hertz. So, I may not need to take data beyond this. Beyond this data does not tell much except that it is more or less constant value, beyond this meaning below this for this system. For some other system it may change. This is one way of representing Bode plot. Another way is to use the real and imaginary. Here it is actually minus imaginary that we want to plot as a function of frequency. If you look at mod z versus frequency or z RE versus frequency, they appear to be same here, at least pattern wise they look to be similar. Likewise, if I look at minus phase versus frequency or minus z imaginary versus frequency, they appear to be somewhat similar. Starts at 0 at the low frequency, ends at 0 and shows a peak. But if we have more complex system, they will not necessarily look the same. This particular example, it appears to be the same. I want you to keep in mind that it does not mean every electrochemical system. If you plot absolute value of z versus frequency and minus phase versus frequency, unless you actually calculate and plot, you will not know what it is for real and imaginary. Now, that calculation we have done using complex plane notation. If I take this and let us call this as E1 and E2 and this is a resistor. So, I represent R1 here, C1, we call it as double layer capacitance. This is called Faradaic impedance, to say it is a electrochemical process, any process where you have a electron transfer, electron participation, that is called Faradaic process. Okay. That may be represented by a simple resistor We can write the equation for this and solve. I am not going to go through that. I will just tell you that it is possible to get a similar expression for E2. Now, that means you can calculate E1 and then calculate the current. In order to get the E2, if you calculate, you would get a time constant now, which depends on the double layer capacitance as well as the resistance here and the solution resistance. Previously, we just looked at one R and one C in series. You have one more R here, and that is going to come into the term which represents tau. Now, the expression is somewhat similar to what you have seen before. Okay. So, you have EIC0, R solution and CDL. Previously, this was tau, but now it is a little more complex expression. You have a sine, you have a cosine, and you also have a transient term. You have to write the differential equation. You will have to say E1 is given by I1 into R. Now, I1 is going to be I2A plus I2B, because any current that comes to this point has to either go as 2A or as 2B. Okay. I2A, you can calculate it saying the potential drop across here is E2. So, dE2 by dt multiplied by CDL will give you I2A. I2B is the potential drop across here divided by the resistor. So, if you use these equations, you can eliminate the remaining terms, and of course, E1 plus E2, that has to be equal to EIC0 sin omega t. This is the applied voltage. You can write a differential equation in E2, and like what we have done before, we can solve and get the expression for E2. You will have to use the initial condition at time t equal to 0, applied voltage is 0. So, my claim is if you do this, you will get this lengthy expression with a tau value related to R and R solution and CDL. Now, if we do this and then I want to plot this, this is no good. I want you to see that it takes more than one cycle for it to settle. This is done at an example of 100 kilohertz at 5 millivolts and 1 ohm of R solution and certain values of CDL and R. E2 given as V2 here, that oscillates, but it settles after some time, which means you can't just say wait for 5 cycles. It usually settles after some time. So, you have to say wait for 2 seconds, wait for 3 seconds, wait for 1 millisecond, some number there. So, this goes from 0 to 0.1 millisecond, almost around this point it settles. So, it comes to steady periodic motion after certain time here. Now, if we change the resistance to 100 ohms for the same system, this is 5 millisecond, it settles after 3 or 4 milliseconds. Previously, it settled much below 0.1 millisecond. Here it settles after 3 or 4 milliseconds. That means, here I am showing only the average value. There are oscillations, goes like this, and then because it is harder to see, I have not drawn that there, I have just drawn the periodically average values. In the very beginning, when I go from 0 to 0.1 millisecond, it looks like it is steady periodic, except that there is a slight slant here. I have to really measure it for a long time to know how long it takes to settle, and if I plot it here, it will be steady periodic. So, when the resistance is higher, this value will be low. If this value is lower, tau value is going to be higher, time constant is larger. When time constant is larger, it takes longer time to settle. Another way to visualize this data is to plot it in what we call as 3D plot. Frequency is in the x axis here, real is in the y axis, and minus z imaginary is in the z axis. Of course, this scale has to be adjusted so that it looks somewhat equal scale. You may not be always able to do that, and the frequency is in the log scale. But if you are able to put it here, you can see this goes like a loop. It comes out like a loop and comes here. So, if you visualize, it starts at a far away point and then it comes towards us and then settles. You can also see how the imaginary will look like. So, one form of Bode plot which is minus z imaginary, and other part of the Bode plot which is z real versus frequency, and the complex plane plot. Of course, this is okay when you plot only one set of data. If you do experiments, you want to say I want to plot at condition 1, at condition 2, condition 3, then you will have 3 sets of data. You can plot them, but you can't really see any difference here. It is just going to be completely mixed up. Now, which format is a better format? Complex plane format, Bode plot with magnitude and phase, Bode plot with real and imaginary. So, there is no one answer for this. What we do is to plot in all three formats. And usually we have an idea of what system we are looking at, what is the phenomena we are studying, and then we look at the data. Usually you want to compare more than one set of data. We look at the data and see which format brings out the point very clearly. Whatever we want to understand from that, whatever we want to say from this, which format brings out that point clearly, you have to use that format for that set of data. You can't just say I will plot only in Bode format and do the analysis. I will plot only in complex plane form. You have to plot in all the three formats. So far what we have done is we have taken a circuit, taken numbers for those values, and then said I want to calculate the impedance. What we normally do in real life is to do experiments, get data, and then say I want to either find a circuit that will be suitable for this or find a reaction that will be suitable for this. Reaction is the next level. First level is to say I want to first know what circuit can be used to represent or model this data. Here we will say we will use this circuit. You can use other sets of circuit by the way to model this exact same data. But let us say somehow we know this is a good circuit for this. Next is, can I find the information of R1, R2 and C2 from this data? I have this data, I want to model with this and I want to get the value of R1, R2 and C2. What is the best fit for this data? It is like saying I have a set of data, I want to fit it to linear equation y equal to a plus bx and find the best values of a and b. If it does not fit, we may try a quadratic equation. If you have a physical understanding, you may try different sets of equation based on what you think is the correct model. So, there are a couple of aspects to this. One is to identify the correct circuit, second is to extract the parameter values from this. Likewise, we want to be able to identify the correct reaction and extract the kinetic parameters from them. That is the second level. So, if I want to extract parameters from this, I want to extract 3 elements. Okay. If I say I want to fit this data to a linear equation y equal to a plus bx, you want to get a and b from this, you need minimum 2 points, 2 pairs. If I want to fit it to a quadratic equation, I need minimum of 3, although it is better to have many more points to do linear regression, but if I give you 1 point, you can get infinite number of solutions for any linear equation. Likewise, absolute minimum I need is 3 elements, I need 3 points, but typically we want to use 50-60 points at the minimum. You have commercial software, you have free software to do this part. It is not that difficult for a simple circuit. For a little more complex circuit, you will have to give correct initial values, otherwise it will not converge. Okay. The next part, which is other techniques.